AI, what makes it hard and fun? If it's easy, then it's not fun, at least from a research point of view. And I'm going to talk about research at Intel Labs. Of course, our job is to look ahead, to push industry frontier as far as technology is concerned, both in the AI space as well as then from a computing standpoint. That's really what research is meant to do for Intel, maintain its leadership. And a lot of the work that I'm going to talk about here, and not many people know this, happens right out of Bangalore, right? So for many of us who believe world-class research doesn't happen in India, hopefully we'll debunk the myth. All right? With that, we heard all of this, right? Compute doubles, or hey, there's data growth, data growth, data growth. I'm not going to give you stats about data growth, but roughly speaking, this is what's happening, right? Compute doubles every 1.5 years, but data is doubling every year. So what, right? What does it fundamentally change? Remember, the world we are used to is on the left-hand side, inside out, right? Now, what does that mean? That's how science was done, for example, right? You start with observations, you build some postulates, from postulates to physical laws, and then from physical laws to we do predictions. But what does data fundamentally do? Data allows you an outside-in view. You don't know anything about the system. You don't understand the equations inside that are governing it. But data fundamentally allows you to model these systems. You could start sort of reverse engineering it. So I'm going to give you a couple of examples. What do I really mean by that, right? But it's a paradigm shift, essentially, right? Now, what else happens? We're used to this world. Machines crunch numbers, humans make decisions, right? If I ask you guys to do 1031 multiplied by 2041, I don't know how many of you will do it. But your cell phone would and you would. That's where you will go. That's the world we're used to. But if we have to make even simple decisions that kids make, humans are in charge. But that's again changing, right? Machines are crunching numbers and making decisions. Of course, we have seen it in the financial world, but in terms of applications, for example, we are talking about autonomous driving. What are you really doing? You're doing a decision offload. You're putting your life in hands of a machine. We didn't do that until now, but that's where we are headed. So therefore, the division of labor between machines and humans is fundamentally getting disrupted, right? And it's very easy for machines to beat us because we are terrible drivers. We text while driving. Low bar, right? It's not really a low bar, but still, right? It's not going to be so hard once machines get there. What does this whole thing do? I mean, this is what drives these 2 or 3 things really drives our research vision. It's the first three foils are really the background foils. We're used to an industrial revolution, right? The world of mills. There is yet another mills coming, and we call it machine intelligence-led services, which is what, for example, the Amazon talked about, machine intelligence-led services, right? We think that world is essentially coming. Now, these 3 foils are the background of what drives our research. Why should we worry about, why is AI an important space for us? Now, let me move to, so what? Now, what do we do from a research point of view? We bucket our research. We have a top-down view of research, right? Starting from science, the actual science, as we talk about it. And not many people would be surprised. Intel doing science, wait a minute, we thought we were a chip company, right? So we're talking about cognition and neuroscience. And I'm not talking about neuromorphic chip that you heard about, Lohi, although we are proud of what we put out there. I'm talking about real science, right? Then computer science. Once we do science, what are the implications from a computer science point of view, from algorithms point of view? Then, of course, comes the systems, right? Our lab, Intel Labs, at least particularly in my lab, actually goes top to bottom, right? I'll give you a few examples, and you will be able to correlate back to your inside out to outside in model and decision offloads and those kinds of things as an example, right? So first example, right? Princeton University, right? Now, this gave us actually our first Nature paper. Princeton Neuroscience is one of the premier neuroscience institutes in the world with billions of dollars. They don't need to come to Intel for neuroscience, right? But they had a problem. Now, what's the problem, right? The goal they wanted to do was, how does the mind emerge from the brain? I mean, it's easy to see how neurons are connected in the brain and build a circuit out of it. But that doesn't necessarily tell you how it functions. Right? How do you know how the brain functions? Right? So we took this challenge 2-3 years ago, and they essentially wanted to understand the software control inside the brain, if you will. Right? What is the instruction set? How does it work? And the problem there was, for example, now they thought they can do it with fMRI data. Now, if you want to do the fMRI data, how long do you keep subjects inside? Right? Human beings are not going to stay there for hours, and that's what it was taking to generate an fMRI image and analyze it. You need it real time. And that was fundamentally their problem, right? And this actually led to our first Nature paper, which is a big deal, right? Nature Neuroscience paper in February 2017. And the idea was, can we open up the black box? Remember, inside out, outside in? Black box. I don't know how it works, but fMRI gives me the data so that I can reverse engineer how mind arises out of the brain. And that's what we are really doing, right? I mean, it's literally, we talk about black holes. This is yet another black hole that we don't understand, right? That sits right here. Now, how do we decode it? That's really what the problem was. Now, we've put out this work. There's a brain imaging kit that's available online, and this work is still ongoing. The challenge here literally is that in 5 years from now, 3 years I think are over, the goal was, you think of a video, we'll play it. You don't need to tell me anything anymore. You think, I tell you what you're doing. So you literally see how decode your mind. Now, that's not the real world application. I mean, it may be, but that's not what you want to do. If you see, for example, treatment of depression, how do I know what's happening inside the brain? That's what I want to fix, right? That's one example. So that's the reason you do these things. Now, of course, for our CEOs to be able to get onto the stage and talk about, you think of a video and a play, good thing. But there are larger things besides that, right? And that's really what the goal of this was. Similarly, for example, this was covered in National Geographic. We want to monitor environment. We've always talked about AI monitoring environments and all of that stuff. And this is real stuff happening out there, coming out of research labs, getting deployed. It was in the CES demo. Our CEO showed it this year. Whale health monitoring, using drones and using AI. Again, was a work done by our labs, right? Again, you can see how fundamentally you can take on problems that were beyond the realm of compute earlier. We never thought of monitoring whale health with compute, for example, right? We never thought of depression in compute. So therefore, you're pushing the boundaries of where compute can go, and in some sense, expanding what industry can address, right? And this is fundamentally why we say this. This is when virtuous cycle of computing happens, because you're solving these hard problems that otherwise were beyond the realm of compute. And now, therefore, you say, because you go on solving these harder problems, the virtuous cycle of computing can happen. This is really what this means otherwise. Otherwise, it's not about the devices that you put in, hey, there's an edge and there's a server and there's a connectivity, right? All right, let's go to the next one, which is computer science, scalable algorithms. Why do we love it? That part, right? I talked about why I love the previous one, but let's talk about why do we love it and what are the challenges in the computer science space? Where are we focused as a research lab on this? Better model building, we've all heard about it, right? Deep learnings, can we reason with less data? Can we augment it with memory? Can we make it explainable? Those are all questions that arise here, right? More efficient and pervasive model deployments. We know that ultimately when we deploy devices, they need to be more energy efficient, higher throughput. All of those challenges sort of come here. We've all heard about reduced precision, right? How low can you really go? Can training stop at 16 bits, or can it go all the way into 1 bit, right? How far can inference go? Those are the questions. And of course, why am I answering those questions? I'm answering those questions because it has implications on computing architectures of future, right? That's ultimately the goal that we have. Push the boundaries of deep learning so that we push computing architectures of future. And then, of course, scaling needs of AI. When we are talking about hard problems like depression, like agriculture, like anything, I need the AI to be faster. How do I make it faster and faster, right? How much, I can only pack so much compute here. That's why I think, we've heard this in the morning as well, this differentiation between AI and HPC is bogus. AI is the HPC, right? It's just a better buzzword, so we'll go with it. But otherwise, AI is the new HPC. AI is HPC. So let me start with the first one, because we want to go faster and faster, right? Now, this is first example. How many of you have heard of Julia? Okay, awesome. How many of you ever thought that Julia is moral equivalent of a MATLAB language, right? How many of you ever thought that MATLAB could run at 1 petaflop? Have you ever run MATLAB beyond a workstation? Here it is. MATLAB or Julia at supercomputing scale. 1 petaflop solving a real science problem, right? We started this work almost 3-4 years ago in our lab. And today, this was a supercomputing paper, I think, where we started looking at the universe astronomy data and being able to generate, build a generative model, see what are we seeing really, right? How are we get more information about the universe. The big deal here was that Julia, which is very easy to use, anybody can use it, can run at this scale. So you don't have to struggle with how do I really optimize. You don't have to worry about the computer science issues of it, right? So this is one way of making AI faster. This was the non-DL example. I wanted to make sure that we don't only talk about DL. But hey, look, here is Bayesian inferencing, right? All right, deep learning. Now, this was the work actually that we've all heard of large batches now, right? But not many of you would know the first work in this space came from us, right? The breakthrough on why large batches don't work came from us, which was why there was a fundamental problem. When you use smaller mini batches, it seemed to generalize better, it seemed to learn better. But when you used large batches, it didn't seem to work. Why not? You had an accuracy gap. So this is the work that we did with Professor Nocedal, actually. What really happens in a large batch is when you take average of gradients, the noise essentially goes down. And then the noise goes down, what we observed was that the deep neural networks learn when you are in a flatter bowl, much wider bowl. That is when you do generalization. But when you are working with much lesser noise, you end up going to a sharper minima. Right? This was our paper, which basically said, hey, look, large batches don't work because you end up going to a sharper minima instead of a flatter minima, right? And because of that, you see, while your testing seems to be going okay, your generalization or your training seems to go okay, but your testing doesn't. And then we showed a technique which we called as a warm start, if you will, and said it was an empirical technique that you train with a smaller mini batch for a few epochs, and then you empirically transition to a larger mini batch. And then the subsequent work from Facebook basically picked on that and said, all right, because we would want to scale in our infrastructure, sometimes I want to scale to 10 nodes, sometimes to hundreds, maybe to thousands. I can't be empirical about it. So they connected it to the learning rate. Warm start reflected in learning rate, right? Which was their contribution. And then we started seeing, hey, large batch training, ImageNet trained in 1 hour, and so, which is awesome. So, one example of us pushing the industry boundary. And then, of course, on Xeon, what does it do? I mean, while others were coding 1 hour, we are also at 44 minutes with same ResNet and enabled by same large batch, right? And this is all supercomputing scale. And this is cloud, for example, right? Now, this is where earlier we talked about, hey, you upgrade to deep learning for free. This is an Ethernet result, which is not an HPC interconnect, available in cloud. 64-node CPU system, Skylake-based. Skylake is barely, not even half of Pascal in terms of its compute capability. But if you compare, and that's really what the difference is, 7.3 hours versus 4 hours, because CPU being general purpose doesn't have as many flops as GPUs have, but scales linearly, 64 nodes, no difference, okay? And you can go more. This is all at 90% plus scaling efficiency. Now, deep learning at 15 petaflops. How many of you have even heard of it? This was our supercomputing paper in 2017, November. Now, again, two science application, Large Hadron Collider, as well as weather application, pattern discovery in climate change. We had built these libraries that you see out there. One of them is called MLSL, which was a SysML paper this time. And we went to 15 petaflops of deep learning, which basically means about, if I'm not mistaken, 9,300 nodes. That scale, right? And look at the kind of speed-ups we have. Tells you the scaling efficiency, right? So what does this do? This basically makes deep learning go faster. Time to train keeps coming down because you can go to these kinds of scale. Now, this is all past. It's a good, okay, well, you're telling me a year-old news. What's new, right? What have you done for me lately? Question my boss likes to ask me very often. We know these two things, right? This, if you followed NIPS in November, ImageNet is the new MNIST. And if you followed Baidu's paper, essentially models today are in the power law region, which basically means the model sizes will continue to grow as more data becomes available. In other words, the need to train faster is not going to go away. Your model sizes are growing, your compute is growing, significantly enough, and we know how model capacity has grown, how training has gone to exaflops of compute. So we still have a problem. We still need to go faster. The question is, can we go faster than large batch? The large batch work that was done, I think we showed it at 16K batch size, Facebook at 32, and then Google at 60, but then we stuck. ImageNet is how much? 1.2 million almost in terms of data set size. But ImageNet is the new MNIST, and data set sizes are going to be larger. What do you do about it? So, can we train faster? Are there techniques that we can? So there are two submissions this year to ICML. They're still not on the ImageNet data set. Hopefully you'll have those results soon. But essentially, can we use second order methods? And this is towards full batch training, where I can use the entire data set as the batch, right? And remember, you have to deal with the same problem. If our conclusion earlier was right, that larger batch size means lower noise, I still need to solve that problem. I'm going to now a much larger batch size. And there are techniques in here. For example, in the first case, the noise is generated by the curvature because you're taking a second order gradient. We use the curvature information to generate that noise. In the second case, it's a progressive batching technique. You train for fewer samples first and then go to a larger sample size within an iteration, then go to a larger sample size within the iteration and generate that noise or get that effect of that noise, right? So there are two submissions this year to ICML. But the moment you're able to do large batch, now your parallelism increases. And therefore, you can go to much larger scales, okay? All right, let me switch the gears. Second part, I have 12 minutes. Arithmetic needs of AI, right? And this is our ICLR 18 paper, which is essentially, we all know FP16 was out there. The question is there any other data type that works? Is there something unique about FP16? Does integer 16 work, right? And does it give any performance benefit over FP32? So these are 4 state-of-the-art CNNs, essentially no hyperparameter change, same number of iterations, same number of epochs, achieving same state-of-the-art accuracy with integer 16, right, which is half precision. And what does it do? It gives you 1.8x over FP32, right? And there are some details on essentially the most compute-intensive parts of this are, of course, in half precision. Otherwise, why do half precision? And that's why you're seeing 1.8x gain. But accumulate still needs to be FP32 or int32, much like FP16, right? And the question still stays here. Remember what I said. Is there something holy about 16-bit? Can I go lower? Right? And hopefully maybe later this year we'll surprise you something more. Hint, hint, right? But looks like you can go more, right? Let's talk about inference. This is where most flops are going to. So far, the state of the art as far as inference, as far as the industry is concerned, is 8-bit inference, right? The question is, can you go lower, right? And there have been many attempts. And again, this is our ICML submission as well. This was in SysML, and we've submitted this work to ICML as well. In an FP32 setting, if you sort of look at this picture, you have sort of, once you've trained a model, you have a set of weights, right? And remember, when you are sort of training, what you're doing is you're going into this flatter bowl. You learned a representation as captured by the weights here in the flatter bowl. Now, when you go to lower precision, what are you really doing? You're really perturbing the solution space, so which is what we call here as W hat, ternary setting. So you had learned generalization here. Now because you ternarized your weights, you added noise to the system and it shifted, right? So solution is not the same anymore. The question is, how do you bring back the generalization without retraining. You can always retrain. In fact, actually, even with retraining, people haven't shown it yet. So this was the work, and we basically developed a theory which we called as perturbation theory. And based on that perturbation theory, we came up with techniques that essentially bridge the gap to the best of our knowledge. This is the first 2-bit weight inference achieving state-of-the-art accuracy on CNNs, right? Same accuracy as 8-bit. And this is the bottom one, the highlighted one is essentially our results. The most important part of all of this is no retraining. Most of the times, whenever people have attempted going below 8 bits, they have always retrained, or otherwise they lose significantly. Even with retraining, there is an accuracy gap, right? Our own experiments were almost 4% accuracy gap, which is significant enough. But the important thing here was no retraining whatsoever. Now, what does it do? Why do I care from an Intel point of view? Of course, it pushes industry forward, but immediately what it does is you don't need floating point arithmetic anymore. Suddenly, on a silicon, I can have, number one, I'm at 2 bits, at 2-bit weights, I only have to worry about adds and not multiplies. I have area power gains, right? And then we had some sensitivity analysis on what if we, because we talked about residual edges, the technique here really was that we have figured out the theory to say, when we go to the lower precision, to 2-bit, because we perturbed the solution, where do we need to add more precision, right? And when I say more precision, I'm still talking about 2 bits, right? So there is an intelligent technique behind where we add more precision, how do we identify that, and what it shows is, for example, if I add residuals 2.5x, I am at 1% loss. If I make it 2.2x, if I want lesser compute, for example, I don't want to, I'm okay with a slightly lesser accuracy, I could even do that, as in I can fine tune my, where I add residue to it, right? And of course, AlexNet is the worst case actually, so ResNet will look much better. I think ResNet gives you about 3.6x power performance gain, but even with something like an AlexNet, you have a 2.43x gain relative to 8-bit, right? Therefore, from a computing point of view, we talked about better throughput, better power. From a deployment point of view, it enables all of that stuff, right? All right. Better model building. So I did talk about autonomous driving as an example. So this was, again, our work at NIPS. One of the ways AI has been taught, or how well can AI learn from expert demonstrations, right? And the state of the art there was something called GALE, generative adversarial imitation learning. The fact that you make AI learn from expert demonstration is the imitation learning, is the space of imitation learning. And if we looked at the GALE worked fantastically when it worked well. But in cases, if you sort of look at the histogram and, if you sort of, it's learning from, I think, 250 plus trajectories, it had heavy tail problem. Essentially, in cases where it failed catastrophically. It had no sense of how to avoid those failures. Now, that's okay if I'm playing a simulator game, right? If I'm playing an Atari game, or if I'm playing something else, that's okay. I can fail as many times as I want. But if I now am trying to teach an autonomous car how to learn from the driver behavior, I'm not sure I can afford those failures. So therefore, heavy tail becomes an important problem to solve. So our solution was, what we came up was rail, right? And again, this was something that we borrowed from the financial world, actually, where I think earlier TCS representative talked about value at risk in the financial modeling. In fact, actually, we borrowed it from there. We reformulated this problem where we essentially, in some sense, are giving it a sense to assess risk, right, of taking a particular set of actions to arrive in a different state, right? And you essentially want to minimize those risks. And of course, lower is better in the case of, so we call it conditional value at risk. We added that to the formulation, and that was essentially our contribution, and is a NIPS and AMAS. Again, you can look it up, right? Risk-averse imitation learning. and converges as fast as Gale. All right. How can you engage with us at Intel? I guess we already covered some of this stuff, software.intel.com. Most of the work that we end up doing in our lab appears to the outside world, to the community, either through the software work we have done, for example, MKLDNN, MLSL. A lot of our work is already in there. So therefore, software.intel.com. And of course, as you see, the new hardware coming from Intel, that's how we earn our paycheck. Otherwise, we won't. So it shows up in Intel hardware. All right, with that, thank you very much.